In this lesson, we're going to go over how we can find the area between curves. So we know how to find the area under a curve that's bounded by the x-axis. We use integrals. So technically, our x-axis is the equation y equals 0. So when we are finding the area under this curve, we're taking the function and we're technically subtracting 0, and we're going from a to b. But what if we want to find the area under a curve that's not bounded by the x-axis? What if we want to find the area as seen below? So we can see that the function here is not bounded by the x-axis. They're actually bounded by each other. So we have the f of x, which is this orange function, and the g of x, which is this black function. And we want to find the area between them. So how we go about doing that is taking the area of one function minus the area under the other function. So here we have the top function is f of x, and the bottom function is g of x. So if we took the area under f of x, that would be from f of x to the x-axis, and you can see that highlighted here in red. And then we took the area of the g function, which is the area under g, to the x-axis as well. And if we subtract those two, we're going to get the area just between f and g. So the integral from a to b of f of x minus g of x is just the integral from a to b of the f of x function minus the g of x function. So we always want to think of it as top function minus bottom function. So it might not always be that f is your top function. It's just whatever the top function is minus the bottom function. So let's look at this example. So find the area of the region bounded by the graphs of y equals x squared plus 3, y equals x equals 0, and x equals 2. So we can see that this parabola here, that's going to be y equals x squared plus 3. We can see the line here, this red or orange line, is y equals x. And then we have these vertical lines, x equals 0 and x equals 2. And those are going to be kind of where it's bounding between a and b. So let's set this up. So we have the integral from a to b. Well, the farthest left that we're using is 0. And the farthest right x value we're using is 2. So it's going to be the integral from 0 to 2. And then our top function is the x squared plus 3 function. So it's going to be x squared plus 3. And then we're going to subtract from that the bottom function, which in this case is y equals x. So we're going to subtract x, and then it's going to be dx. So top function minus bottom function. So if I go ahead and simplify this a little bit, I'm just going to put this in order here. So x squared minus x plus 3. If I take the antiderivative, this is going to give me 1/3 x to the third minus 1/2 x squared plus 3x. And I'm going to evaluate that from 0 to 2. So just like we did before, we have this definite integral. So we found the antiderivative, we plug in the 2, and we plug in the 0. So I'm just going to show that really quick. Plug in the 2. We're going to then plug in our 0. And when we do that, that's just going to give us 0 for everything. So we end up getting 20/3 as our area between the curves. So here we're going to look at another example. Find the area of the shaded region. So here we can see that the upper function is e to the x, and the lower function or the bottom function is x e to the x squared. And we can see that our bounds are going to be farthest left is 0, farthest right is 1. So we're going to say that the area is equal to, so we're going to have the integral from 0 to 1 of the top function, which is e to the x, minus the bottom function, which is x e to the x squared, dx. Now we're going to take the antiderivative. So if I take the antiderivative of e to the x, that's going to give me e to the x. But now when I go to take the antiderivative of x e to the x squared, I have to use u substitution. So I'm going to do that over here. So if I have x e to the x squared dx, the first thing I have to do is figure out what u is going to be. So here I'll say that u is equal to x squared. That's my innermost function here. So my du is going to be 2x dx. And I can see that I have the x dx, but I don't have the 2, but that's fine. So I'm going to pull out that 2 by dividing it. So I'll have 1/2 the integral of e to the u du. So now when I take the antiderivative of this, I'll have 1/2 e to the u, and then, plus c, but we're using a definite integral, so we don't need the plus c. But we have to change the u back, so this would really be 1/2 e to the x squared. So that's what I'm going to use here. So this is minus 1/2 e to the x squared, and then we're evaluating this from 0 to 1. So what I'm going to do here is just plug the 1 in. So I'm going to have e to the first power, which is e, minus 1/2 e to the first. So that's minus 1/2 e. And then we have to plug in 0. So e to the 0 is 1. And then minus 1/2 e to the 0. So that's just half. And then we end up getting 1/2 e minus 1/2. Okay, so we're going to look at this other example here. So find the area bounded between the graphs of f of x and g of x. So here we don't have a picture of the graph, but that's okay. We can kind of figure out what it looks like since we know what a parabola looks like and a straight line. So the first thing we want to do is figure out kind of what this is going to kind of look like. So we have our normal function, x squared minus 5x minus 7. So that's going to be a positive parabola. So it's going to look, something like this. That's pretty bad. And then we have a line that's x minus 12. So I'm just not drawing anything to scale, but whatever, something like this. So they're going to intersect at some space, and we're going to have this little area between the two. So to figure out where they're intersecting, we need to set them equal to each other and find out what x values that would give us and y values. So let's take the first function, x squared minus 5x minus 7, and set it equal to the second function, x minus 12. So we want to solve this, and we need to bring everything to one side. So since we have a quadratic, so I'll have x squared minus 6x plus 5 equals 0. And now we're going to factor this. So this is going to give me x minus 5 and x minus 1. And then we're going to set each to 0. So x equals 5 and x equals 1. So those are going to be my x values. I could plug them back in to either of the two functions to find the y value that matches them. So 5 negative 7 is 1 and 1 negative 11 is the other. So let's just, this is very not well drawn, but pretend that that's 5 negative 7. And let's pretend that this one, this one is, flip-flop. So let's pretend that this one is 1 negative 11 and that this one is 5 negative 7. So not drawn great, but you get the idea. So now if I want to find the area between the curves, I can see that my bounds are going to be from 1 to 5. And my top function is going to be the green one, which is the line x minus 12. And then I'm going to subtract the bottom function, which is my quadratic. So this is going to be minus x squared minus 5x minus 7 and dx. So what I can do here before I take the antiderivative is I could actually just simplify this a little bit. So I'm going to just combine like terms. So this is going to end up giving me negative x squared plus 6x minus 5 dx. So I just combined my like terms there, and now I have something a little bit simpler. So now I can take the antiderivative of this, which would give me negative 1/3 x cubed plus 3x squared minus 5x. And then we are evaluating it from 1 to 5. So just to kind of make things a little bit shorter, to plug in the 5 and to plug in the 1 and subtract them. So we end up with 32/3, or if you wanted as a decimal, 10.667. All right, so then we're just going to look at this question, which this one is actually a calculator question. So it's important to know how to do it by hand and with a calculator. So depending on what section something like this might come up with on the test, you know how to do it both ways. So find the approximate area of the region bounded by this curve and that curve. Okay, so it's kind of hard to graph it. The other one that we just did was a little bit easier. We know what those shapes look like. Here, we're not really sure what this function might look like. So let's go to our calculator. And what we're going to do is plug in. I already did that in here. So in my y1, I'm going to plug in one function. And then in y2, I'm going to plug in the other function. So what I'm going to do is graph them. Okay, so I can graph them here. So by looking at the graph, I can see now what the functions look like. I'm just going to go back really quick. So the blue function is the first one, and the red one is the second one. So I can see that the top function is the blue function, which is the first one. And then the second one, or the bottom function, is the red function, which is my second function. So in order to figure out where they are intersecting, I can see that they intersect at 0, but let's use the calculator to help us. So second trace, and we want to find the intersect, so I'm going to go to number 5. Okay, I can do the intersection at 0, and it's going to give me 0, 0, but the one I really don't know is right over here. So I'm going to go to about that area, and then I'm going to hit enter for the first curve. It wants to know, is this the second curve I want to use? Sure is. Hit enter again. So it tells me that intersection is 1.181, comma 0.763. So since I know that intersection, let me go back to over here. So I have two intersections. I have 0, 0, and I have 1.181, comma 0.763. So those are my 2 points of intersection. Since I'm dealing with the x's, I'm going to say that my area is equal to the integral from 0 to 1.181. And then I knew that the top function is the x over square root of x squared plus 1 minus x to the fourth minus x. Put in my dx over here. So what I can do now, just to figure this out, instead of doing antiderivatives by hand, I'm just going to use the calculator. So I'm going to go back to here. I'm going to go to my main page. So I'm going to do the integral. Oops, and I went right past it. Okay, so I'm going to go to the integral from 0 to 1.181. Okay, and then the top function I had saved in y1, so I'm actually just going to call that again. So I'm going to call that, it's y1 minus, I'm going to call the next one, which is stored in y2. So y1 minus y2. If you don't want to do that and you want to type in the functions again, by all means, go for it. But I don't think that you might want to because of time, especially. So then we're going to hit enter. And then it tells us the area is 0.785. So let me just go back to here and I will just write that in. So 0.785. Okay, so whether or not you're using a calculator, you can still figure out the intersection points and then subtract the top function minus the bottom function. Sometimes you might have functions that kind of flip which function is on top and which function is on bottom. So that we can figure out by using the absolute value. So when you have the absolute value of the top function minus the bottom function, that's going to always be dependent on which function is on top and which function is on the bottom. So for instance, here it says when f is larger than g, so when f is on top, you're doing f minus g. But when g is larger than f, so when g is above f and g is on top, then you're going to use g minus f. So it's really just always the top function minus the bottom function. So let's look at this example, which says to find the area of the region bounded by the curves y equals sine x, y equals cosine x equals 0, and x equals pi over 2. Now notice here there's two different areas, and they're kind of shown to you here. In area 1, the top function is cosine, the bottom function is sine. But then after we pass pi over 4, it switches, and the top function is then the sine, and the bottom function is the cosine. So what this actually is like the absolute value. So we're going to say the area of the integral between 0 and pi over 2 is going to be the absolute value of cosine x minus sine x dx. Okay, so we have to split this up. So we always want the top function minus the bottom function. So from this A1 area, we can say that the area is equal to the integral from 0 to pi over 4. So we're only looking at this blue region. So 0 to pi over 4. The top function is cosine x minus the bottom function, which is sine x dx. And then I'm going to add the integral from pi over 4 to pi over 2, and that's this orange region here. And the top function is going to be sine. Sorry, I'm smushing this in. Sine of x minus the bottom function of cosine of x. Oops, sorry, dx. Okay, so what we did is just kind of split it up. So we're going to do each one separately. So we're going to look at the first integral from 0 to pi over 4. We're going to take the antiderivative of cosine x. So that's going to be sine x. And then the antiderivative of sine x is going to be negative cosine, but we have that minus. So plus cosine x. And we're going to evaluate that from 0 to pi over 4. And then we're going to add that to the antiderivative of sine x, which is going to be negative cosine x. And then the antiderivative of cosine x is going to be sine x, but it's minus there, so minus sine x. And then we're evaluating that from, pi over 4 to pi over 2. So if we plug in, let's change colors. So sine of pi over 4, so I'm just going to go over here. So that's root 2 over 2. Plus cosine of pi over 4, so that's root 2 over 2. Minus, do this in a whole big thing. So minus sine of 0, which is 0, plus the cosine of 0, which is 1. And then we're going to add to that the next integral here, or the antiderivative, plug it in. So we plug in pi over 2. So negative cosine of pi over 2 is going to be, put that in a bracket there. That's going to be 0. And then we have minus the sine of pi over 2, which is 1. And then minus plugging in pi over 4. So negative cosine of pi over 4 is negative root 2 over 2, minus the sine of pi over 4, which is root 2 over 2. Okay, so we plug everything in correctly. Great. If you go ahead and simplify this, we end up with 2 root 2 minus 2 as our final answer. So there's one other way to find the area between curves. So what we've been looking at so far was top minus bottom. But what happens if we're trying to find an area where there's not really a top function and a bottom function? There's more of a right and left. So when there's a right and left, we are going to treat it as far as x as a function of y instead of y as a function of x. So here we would have the area between the two functions pictured here would be the right function minus the left function, so f of y minus g of y. And in this case, instead of going from a to b, they're going to go to c to d. So this is really like the point AC, let's say, and this is the point BD. So normally we go from a to b, we do it in terms of the x's, but we only go in terms of x's if we're doing the top function minus the bottom function. If we're doing the right function minus the left function, we have to do it in terms of c to d, which is the y values that we're looking at. So let's look at an example. So find the area enclosed by the functions x equals a half y squared minus 3 and x equals y plus 1. So you'll know pretty much if you have to use the right and left or the top and bottom. If the functions are given to you in terms of x, if they're x equals, you're going to be using right and left. You can change the functions to make them x equals if you want to use right and left instead of top minus bottom. Most of the time we'll be using top minus bottom, but here's a case where we're going to use right minus left because it's in terms of x equals already. So here we have the area equals the integral. So we're doing the bottom to the top because we're doing the y values here. So that it's going to go between -2 and 4 because those are our y values. And then we're doing the right function minus the left function. So our right function is going to be y plus 1. And then we're going to subtract from that the left function, which is 1/2 y squared minus 3. And now we're going to have dy instead of dx because it's in terms of y here. So we get the integral from -2 to 4. And just to kind of clean it up a little bit and simplify, we have -1/2 y squared plus y plus 4 dy. So now all we're doing is taking the antiderivative. So this is going to give us -1/6 y to the third plus 1/2 y squared plus 4y. And we're going to evaluate that between -2 and 4. So you guys know the drill, plug in 4, plug in -2, subtract them. So we end up getting this equals 18. The last example we're going to go over is how you can find the area using two different methods. So most of the time you're going to see a graph of the function. So sometimes you'll have to graph it in your calculator, but a lot of the times you'll be given the graph. So sometimes it's hard to know if you should use the top minus the bottom or the right minus the left. So I'm going to show you a problem here where you can do it either way. So we have R and S, which are two regions, and they're bounded by these functions, tan x and 2 minus x cubed. So here we want to find the area of R. So if I look at R, I'm just going to highlight it real quick. All right, I'm trying to find this area. Now, if I'm trying to do top minus bottom, all right, we're going to do top minus bottom first. If I'm doing top minus bottom, I can see that when I go from 0 to whatever point this is, the top function is the tan x. The bottom function is going to be the x-axis or the line y equals 0. So as I'm going, I can see it's top minus bottom, tan x minus 0, tan x minus 0, tan x minus 0. Once I get to this point of intersection here, the tan of x is kind of gone from this R area, and my new top function is this 2 minus x cubed. So 2 minus x cubed minus 0, 2 minus x cubed minus 0. So we have to split this up into two different integrals that are going from different x values. So what I'm going to do here is just, here's this one, and here's this one. So the first thing we have to do is figure out our point of intersection here, as well as finding out this point here. Because if I'm going from left to right, I know I'm starting at 0, but I'm going to this x value for the first integral, and then I'm going to this x value for the second integral. So what I'm going to do is just plug this right into my calculator. So if I go to y equals, I already put them in there, and I'm going to hit graph. So I can see that I'm focusing right here on this region, and the R is going to be right here. So I have the tan is my blue function, and 2 minus x cubed is the red function. So if I want to find my point of intersection, I'm going to do second trace, go to intersect, and then I'm going to just pick those two curves. So I get a point of intersection of 0.902, comma 1.266. So I'm just going to go back to this one over here and just write it down. So I have this point of intersection is 0.902 and then 1.266. Okay, I also want to find this point over here. So again, I'll just go to this. So to find this, I'm looking for my x-intercept. So I'm going to go to second trace, and I'm going to go to 0, which is number 2. And I don't want that curve, so I'm going to hit down. This is the curve I do want. Go above, I'll go below, and hit enter. So it tells me that that 0 is 1.260. So again, I'll go back over here, and I'm just going to put 1.260, comma 0. So now I have all of my intersection points. So if I'm going to do top minus bottom, the first integral is going to be going from 0 to the x value of this intersection point, which is 0.902. The top function is going to be tan x, and the bottom function is 0, so I don't really need to subtract 0 from that, so I'm just going to tack on the dx. And then what I'm going to do is add to that plus the next piece, which is the integral from where I left off, which is 0.902, to the x value that it stops at, which is 1.260. And then I have the top function in this case, which is 2 minus x cubed, minus the bottom function, which is 0, and then dx. So I am just going to plug this right into the calculator. I'm just going to use that math9 function, plug in my bounds and my functions, and I can use the functions I already stored in the y equals. So if we do that properly, this should equal 0.729. So now let's say that we wanted to do right minus left instead of top minus bottom. Because when we look at this, we can see that as we go from 0 to 1.260 here on the x's, that the right function minus the left function is going to be consistent all the way throughout. So what we're going to do here is look at the right and the left. But the problem is that when we're doing right minus left, we have to make sure that we write our functions in terms of x, or in terms of y instead of in terms of x. So when we have the function y equals tan x, if I want to make it x equals something with y, I have to solve for x. So if I'm solving for x, x is going to equal the inverse tan of y. So I'm just going to box that for a second. So we're going to use that function. We also have y equals 2 minus x cubed. So what I have to do here is again solve for x instead of y. If we do that and we solve for x, we get that x is equal to 2 minus y to the 1/3. Okay, so all we're doing is solving for the other variable. So now when I go to use the functions, I have to use these functions instead because they're in terms of y. So here we would have the area would be the integral from, and now because we're going right minus left, our integral has to go from the lower y value to the upper y value. So my lowest y value is going to be 0, and my upper y value is going to be this 1.266. So the integral from 0 to 1.266 of the right function, which was this y equals 2 minus x cubed, but we changed it in terms of y. So it's going to be 2 minus y to the 1/3. Put that like that. Minus the left function, which was tan x, but when we solved it in terms of x equals in terms of y, we end up with inverse tan of y. And then we're going to have dy because we have the y variable that we're using. So if we plug this into a calculator, this is also going to equal 0.729. Okay, so we're going to get the same exact answer, but we did it a different way. So you can do top minus bottom if you want to, but you're going to have to split it up into two separate integrals. This one would actually be easier to do right minus left, but I guess the issue with doing right minus left is that you have to make sure that you solve the functions in terms of y instead of x. So either way, there's some extra work that needs to be done since it's not just a straightforward, simple problem.